light and matter, interacting in the world around us, from reflections in the mirror to the green grass beneath our feet. But do we know everything about the spectacle that is light? Deep within a laboratory, a careful process takes place. One wrong move, and it could be back to the start.
So if you got a human hair in there, then the cavity would be ruined.
Professor Jenny Clark from the University of Sheffield has spent her career working on light and its properties.
How we interact with it, we can feel the light, so you can feel the tingle, the sun on your skin.
But the question of what light actually is has plagued scientists for centuries.
So light is the basis of all life, I would say. So light comes from the sun, and it gives rise to it generates energy in the plants that we eat and that the animals that we eat. On one side, you can talk about light as being a wave of electromagnetic radiation. Then the light comes in little particles of energy.
Those packets of energy are called photons, the smallest light particles. When a material absorbs light, photons excite tiny molecular particles called electrons to a higher energy level. The electron and the gap in its molecule it leaves behind are known as an exciton. But it seems excitons can behave in peculiar ways. When light is trapped in a microcavity, a chamber of tiny mirrors, the photons and excitons strongly interact and are coupled together. Enter the polariton, neither light nor matter, but somehow both at the same time.
In polaritons, the photon and the exciton interact strongly. And so that means that you get an interaction. So you have the photon is there, and then you have an exciton, and then a photon and an exciton.
If the exchange of energy between photon and exciton is quick enough, you get a quasi-particle. What's so fascinating about these hybrid polaritons is that they display an interesting combination of properties.
If you combine the two, so you get the properties of light and the properties of electrons, of excited electrons, of excitons, then you have the properties of both. So they can travel extremely fast, but you can also interact with them.
Polaritons can transfer energy across much larger distances, and it's their interactivity with materials which makes them ideal for other purposes. I went to the lab with Rob Gordon, PhD student at Sheffield, who's working on these polaritons.
Polaritons are, they have exciting new properties because you combine a matter part with the light part.
For Rob and Jenny, the properties of polaritons make them an ideal candidate for use in solar panels. Turning energy from the sun into electricity, solar panels are crucial in the fight against global warming. But they may lack efficiency, so the potential rescue could be these nifty polaritons.
The main thing that you do to improve the efficiency of some of these new solar cells is a process called upconversion. Where you convert low energy light, so for example near infrared light, into higher energy light, so for example green light.
Solar panels can be made more efficient by increasing the energy of parts of the light spectrum which normally can't be absorbed. Upconversion, also known as triplet annihilation, is one way of doing so.
The nice thing about polaritons is that you can actually enhance this overall upconversion process. A polariton will enhance the absorption of light and therefore the efficiency of solar cells.
Researchers think that maximizing this process could boost the efficiency of solar panels by 13%. But what does this mean for the future of renewable energy?
Well, we're in the middle of a climate crisis, and we need to do everything we can to move away from generating so much carbon dioxide and greenhouse gas emissions. And solar energy is definitely going to be a part of that.
And obviously solar cells have their own sort of material cost, but if we can improve the efficiency of them as well, then we can reduce that cost too. And so that would also improve their viability.
Solar cells are a force for the future of clean energy. But as we now know, they could be improved.